Okay, so today's been a little bit jacked up. I make an unexpected run to the minor emergency center. But, yeah, it's a weird deal. Wednesday evening, I had this horrible pain in my side, but then it went away. And I was fine yesterday, and I was fine this morning. And then about halfway through the first block, like you were stabbing me in the side again with a red hot poker.
Oh gosh.
Are you the reason there was an ambulance out for?
Huh?
Are you the reason there was an ambulance?
No, that wasn't me.
No, there's something else.
It wasn't that bad.
Yeah, there's a
Well, Bert, what
I
caused
assumed
it?
it was.
I don't know. So I went down,
Basically,
did a CT scan, did a bunch of blood work, and they said, we don't even know what's wrong with you. You're taking some antibiotics. That's literally the diagnosis.
Good diagnosis right there.
Yeah, they were.
Okay, so let me translate what that means is that I guess everybody just shut up today. Okay? Don't talk. That's all I ask. Shut up. Love you all to death, but I don't want to talk over anybody today. All right, so let's talk about some of these questions, like let's say, for example, question number 25. So the whole point of this story, and this is going to make sense in terms of what we're going to do today with something called the photoelectric effect. And it sounds weird, but to understand the structure of atoms, you have to understand light. Okay? That's the whole key to this, because atoms in and of itself we can't observe. But if we can figure out the information that they're giving off by the light, then we can know what's going on inside the atom. So here's the main idea if you're looking at atoms. This is what we talked about yesterday. So you have this extremely small nucleus. Now, historically, once they figured that out, and you have to remember, even though the chemistry department always talks about the atom, oh, here's orbitals and all of this good stuff. Everybody that did the work on this thing was in the physics department. Okay? The chemistry department were trying to figure out how to purify cocaine. Right? And the reason that the physics department took it on is because they were basically out of a job. They had figured out the universal gravitational constant. They had figured out Maxwell's equations, although they really didn't know what was going on. We thought we were the only universe, like in the entire universe, we thought we were the only galaxy. We didn't know there were other galaxies. We had no idea of dark matter, dark energy, the structure, anything, protons, electrons, nothing like that. And so historically, science at that point in the late 1800s, early 1900s, was viewed as a dead end because they literally thought we figured everything out. Their only thought process was we need to find out better ways to tweak the constants. Can we find a better way to measure the gravitational constant, the electrostatic force constant, that type of thing, Avogadro's number. They literally were, like we have worked ourselves out of a job. There's nothing left to discover. So when they said, well, let's do this. All right, Rutherford was a physicist. I told you the story before. Physicists like to smash things. You give them a Volkswagen Bug, they smash it into a wall. What flies off? The engine. Oh, let's get the engine up to like 3,000 miles per hour and run it into another engine. Oh, look, a piston came out. Oh, what's the piston made of? I don't know. We'll get the piston up to like 30,000 miles per hour and we'll smash it together. Oh, look, there's particles that make up the piston. What are we going to do with that? Smash them together. Well, that's basically how particle accelerators work. Okay, is you smash stuff together and you see what goes flying off of it. So when they discovered the nucleus, and they had to come up with a new force, they had to come up with a strong nuclear force because the electrostatic force should push these things apart. So if we ever lose, if the universe ever loses the strong nuclear force, very bad things are going to happen. Because every nucleus that exists in the universe is going to go flying apart. Because your protons don't want to be near the other protons. So they said, oh, this is cool. They were physicists. They said, oh, we're going to treat the electrons like planets. Because they said, cool, they had all studied astronomy. They said, we're going to overlay this thought process of the matrix of the sun being the nucleus and the electrons being the planets, and we're just going to make it look like a small solar system. So if you look at the first models of the solar system, like the Bohr model, that's how it's drawn, because they were physicists. Great. But here's the problem. This won't work. And one of the things that they had to figure out was the emission spectrum of light. So we briefly touched on this yesterday. Each element has its own unique, like, fingerprint spectrum of light. Okay? And so what they had to figure out is, like, why? Why are there distinct amounts of light? Why isn't this just a continuous spectrum? And so this deepened the mystery. So, quick refresher to Chem 1. The only way light can be emitted is if an electron moves from its ground state to a higher state and then back down. But here's the weird thing. The electrons don't actually physically exist in between the two quantum states. So that would be like me being on the ground floor. Okay, so this concrete here, that's my ground floor. This is where I'm at peace. Okay, so I could move to a higher energy level like the tables. Okay, great. All right, but here's the weird thing: is like, okay, you're going to have to give me a certain amount of energy, but then I'm going to cease to exist. And then all of a sudden, I'm going to reappear up on the table. Like, you would not see me physically transition from the ground to the table. Okay? Would not be there. But then you'd see me appear at the table. I go, whoa, that got really fast. But then I'm going to go, hey, this is kind of outside my comfort zone. Okay? I'm going to jump back down. But then I would disappear again, and then I would reappear on the ground level. But I had to lose that energy. And I would lose that energy in the form of light. So let's say another state might be on top of that counter back there, that wooden counter. Okay, those are higher. So that would be a higher energy jump. But to make that happen, I'd have to get a higher and higher energy. So this created, hello?
How are you?
I'm good.
That's good.
I just thank you for taking care of us while Bert was gone.
Shut up, Nathan.
That's valid.
Put your hand down. You have questions.
Yeah, all right.
You're not dead?
No, I hope not.
Mara just told me your funeral is tomorrow.
Really?
Yeah, that's what she said.
I didn't get that memo.
Oh, I said, is
Are you gonna be
his
there
birthday
tomorrow?
back or is he dead?
Can I
She goes,
write
he's
you a
dead. His
obituary?
funeral's tomorrow.
Great.
And then I said, I have prom.
Someone can't have a funeral
Yeah, you
tomorrow,
can have
is
it on
that what you're saying?
You're just such a saint. I feel like we should have your funeral on a Sunday.
Uh,
It's like a
no.
nice Sunday mass.
No,
Stay
Saturday, then go have a big party Saturday night.
And then go to confession Sunday morning.
There you go.
That sounds like my kind of, that's a vibe.
Yeah.
Wait, Bert, you going to Africa? Go gamble with us?
Oh, God,
Yes.
no. That's so past my bedtime.
Look me in the eye and tell me you really thought Stan Burkham stayed up till 11 p.m., let alone 1 a.m.
Oh, I did stay up to 11.
You could.
But
He
I
stays up till 11, so he'll be at prom, so you better come dressed up. That's what I
Oh,
heard.
so he'll be at.
Oh.
Bert.
Wait, you're gonna be at prom?
Mr. Burkham's gonna be at prom, you guys didn't know that?
No,
Wait, actually,
Whoa!
Yeah,
dress is you.
What?
Bert, can we have some photos of you?
Yeah,
Please,
please.
please.
I'll see what I can do.
I'll see what I can do. Dude, I love that.
I want to sign.
No, I'm fine.
I want to have a.
They don't know where
I'm thinking about that person. So I can see them.
Not as bad.
That's what I did today.
No.
Okay, anyway, so back to our story.
So
So,
there I was.
yes, ma'am.
So is like going from one place to the other, like as if you get like a certain amount of energy or you lose a certain
Exactly.
you're like teleporting?
So I can't, like, if you look at this as like the analogy of the table, okay? So I can't get enough energy to go like halfway and then come back down. either I gain enough energy to jump from this quantum state to the next, or there's nothing.
So like if you reach a certain level of energy or you reach a certain level, you like teleport from one place to the other.
Yes.
Okay.
So let's say yes.
Wait, so do they go, so if they go to like the third quantum level, do they go to the first one and then the second one?
It
and then the
depends
third
on
one?
how much energy that you're given. Generally, on the way up, you don't stop in between. Like you go from like here to the chair, or you go from the ground state to the table. You don't stop in between. On the way up, you can stop on the way down. You can stop at different levels on the way down, but on the way up, it's a one-way deal. We'll talk more about that later. Okay. So here's the point of the story. Then you had to figure out how do you calculate the energy that's associated with that. Okay, well, E equals h nu. You can also roll this into, since C equals lambda nu, I'm in old style mood today. So nu equals C over lambda. So you can put that in there and you go E equals hc over lambda. Okay? Now, the hc part of this is a constant, because that's Planck's constant times the speed of light. So this is why up here on this, they actually have sought that if you're going to go that route, they have given you hc as 1.99 times 10 to the negative 25th joule meters, and then they also have it as 1,240 electron volt nanometers. Right? So if you want to shortcut this process, if you know what the wavelength is, but again, you have to pay attention to the units. So the beauty of the 1240 electron volt nanometers is that you can just leave the wavelength in nanometers and it gives you an answer in electron volts. Remember, electron volts are just another measurement of energy. So here's the point of this story, is that if you can figure out what energy of light is emitted, then you can figure out what the quantum states are within the atom. So I won't do this as much as I care for you all, but visualize this. We darken the room. You all can't see anything. And I'm going to move to a different quantum state which you all can't see. But what's going to happen is that when I jump down from a quantum state, I'm going to land. And basically, the louder the thud when I land, the bigger the quantum state was. So if you hear that, you go, okay, hey, Bergkamp moved from, wasn't much energy, he wasn't at a real high quantum state, he came back down to the ground level. Now you hear, thump! Ow! Okay? You got, even though you didn't see what happened, you got to figure, wow, that was a lot more energy involved. Bergkamp fell from flipping ceiling. Okay? Now, so we can't see the structure of the atom, but we can study the light. So here's what I want you to see. So if you look at this question on 25 about the arc welding, okay? Arc welding uses extremely high current, okay? And it emits light in the ultraviolet. So you have infrared, and that's what you feel as heat, okay? That's really, really long wavelength. And then you have a very, very, very narrow band of the entire electromagnetic spectrum that we can see. And that's that Roy G. Biv. So you start over here at red, and you end up over here at violet. I'm just going to talk about the extremes. So red light has an extremely long, for the visible light spectrum. Red light has the longest wavelength. So since it has a long wavelength, what do you know about the frequency?
Down.
So that has a smaller frequency, so that also has a
Bigger wavelength.
smaller energy. So if you see red light emitted in a spectrum, you got to figure, oh, that's a relatively small energy jump, okay? So as you guys, that would be something like this, okay? Not much of a little jump, all right? Okay. Now, you see violet light,
Ooh, that frequency's hot.
which has a relatively short wavelength. So that means that's going to have a higher frequency, which means that's going to have a higher energy. So this is why your fireplace glows red right before it goes out. It doesn't glow green, it doesn't glow purple, it glows red, because that's like the last visible light that we can see. Now, it's still hot, you can't see it, but if you put your hand there, you'll feel that as heat. But that's in the infrared region that you feel as heat.
You know, like the blue fire, and then there's like the red, like final light, right?
Yeah.
The bottom of it's like blue, kind of, or a
That,
burner.
so the, like, if you look at like on a
Like a stove.
Bunsen burner,
Yeah.
and you have that inner blue cone,
Yeah, that's what-
that's the hottest part of the
Just
flame.
because like it hasn't dissipated yet, like it's getting the atmosphere around it.
Yeah, but that's just because to emit blue light just requires a tremendous amount of high energy. Okay. So, when you get to, on those questions, like 36, how many photons are emitted during 5 seconds of operation of a red laser pointer? Right? So, power, and this is what you're talking about because it has the milliwatts. Power is basically the number of particles that you kick out, which makes sense, all right, and per unit of time. So if you look at the units, so this is energy, which is photons, or excuse me, which is energy per photon. So then when I multiply energy by photon, by the number of photons, I get energy. And then if I divide that by time, I get joules per second, which is watts. Okay? So, your answer to 36 should be 4.5 times 10 to the 16th, which is D. Now, that's a big number. Okay? So what that means is that, and that's this is only 2.8 milliwatts. This is like a little red laser like we use in class. This isn't like, hey, I want to shoot down an incoming missile, and I'll shoot it with my little red laser, okay? But that's a big number, right? That's 4.5 times 10 to the 16th, and that's photons per second. Now, here's the problem in trying to come up with, to get that number from Planck's constant. The problem with that is that you have two things that are problematic in trying to get that value. Number one, it's a really, 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 really small number, okay? And then also, how do you count photons? Because right now, you all are being bombarded with literally billions upon billions upon billions of photons, okay? And they carry a certain amount of energy. Okay, they do. But it isn't like they turn on the lights and everybody, okay, brace yourself, I'm turning on the lights. The lights are coming on. Okay, like it's some kind of nuclear blast. You are getting hit with photons. You go out in the sun, you're getting hit with photons. Well, it's the only time you're not getting hit with photons.
Dark time and dark.
Yeah, when it's at night. Okay? Right? That's the only time you're really photon free. Every other time, you're being bombarded with photons. Knock, do you have a question?
Question 32.
Okay. So, question 32. So, reduce the area beam by a factor of 2. By what factor does the amplitude of the electric field increase? So, when you get to 32, you have intensity is power divided by area. Okay, this is just a generic way to start with intensity, right? And power, if you look at that area, is 4 pi r squared. Okay? So, if you look at what's happening here, you're told on 32 that you want by what factor does the amplitude of the electric field increase? Well, you also know that this is one of those equations that I gave you yesterday, that energy equals 1/2 C epsilon naught times the electric field squared. So you kind of have to go through stages. So on 32, you've got reducing the area of the beam by a factor of 2. So this area, not the radius, the area is going to go down by a factor of 2. Okay? So what that means is that this is going to become more concentrated. So instead of having a big area, we're going to have a smaller area. So what's going to happen to the intensity?
Double.
It's going to double. So you're going to double the intensity. Then look at what happens, because you're not going to change the speed of light, and you're not going to change epsilon naught, because those are constants. So then, if you double that intensity, well, if you doubled the electric field, and that squared, what would happen to the intensity? It'd go up by a factor of 4. I'm just saying, if you doubled
Oh.
If you doubled E naught,
Yeah, fair enough.
your intensity would go up by a factor of 4.
That would make sense.
Okay?
But we're doubling I.
Yeah, we're doubling I. So you have to figure out what's going to happen to E naught. You're going to have to take that through a series. Your answer to problem 26 should be something times 10 to the negative 8th. Your answer to 40 in electron volts would make a not so good GPA. Your answer to 42 in nanometers should be around 300.
Sorry, repeat that one.
Around.
For which one?
I didn't say how
300 for
small,
what?
how big around. I just said around.
42. Hey, Bert, for 42, I got 5 times 10 to the 14.
You're on. There's no drop round.
Which doesn't make sense.
Yeah, that's
And what did you get for 40?
Oh, now, let's talk about question 47, if nothing else, or problem 47. If nothing else, just because it's a cool calculation to do. So, if you look on question 47, you're given the intensity of electromagnetic radiation from the sun, 1.37 kilowatts per square meter. Average wavelength is 680 nanometers. Find the number of photons per second that strike a 1 meter solar panel directly facing the sun on an orbiting satellite. So, if you do 47 right, and it's just kind of a rearrangement of the equation, you get like 10 to the 21st photon.
I got that.
Okay? Yeah. And so, and here's where this is kind of cool. Okay? This is the number of photons hitting this thing per second.
Bro, how do they count that fast, bro? Yeah.
Wait, what was the hint for 42?
Around 300.
Like 300?
Huh?
300 meters?
Nanometers.
What did you get?
Wait
Did you
a
get 5 times 10 to the 14 meters?
No, I got 10 to the negative 14.
I got it wrong.
It's like,
I got 3 even.
Okay.
I don't know.
Which one? On 42?
3 e to the negative 7.
Okay.
Maybe
So, on 42, let's just kind of go through this since there seems to be some discretion on this.
yeah, I'm kind of confused.
Okay? So, let me give you a hint. Start with this. E equals 8c over 8c over lambda. Cool with that.
I got
Took
that.
a long way around this one.
Right? E equals 8c over lambda. So, you want to know what's the wavelength of the photon whose energy is twice that of a photon with a 600 nanometer wavelength. So, you want this energy to be twice as much.
Yeah.
Can you change the HC part?
Alright, that's constant.
So, mathematically, what do you have to do to lambda here to make it where you get twice the energy?
Whoa.
Yeah. Ooh.
Wait, is that it?
Bird.
Is that all I do?
Yeah, that's all you have to do.
I did, yeah, I took a long way.
Yo,
I
what-
put numbers
what
in
was I
there.
Literally,
doing?
that's all you have to do. So you actually don't have to do any math at all.
Well, yeah, but I
So-
forgot to write down that equation, so basically just derive it.
Okay. On 68, so a little bit of background on Voyager 2. This is the first one, the first probe that we really sent a long way away. A long way away. So the problem with space probes being that far away is that when we send that signal from Earth, and because that signal spreads out at 4 pi r squared, that signal gets real diffuse real fast, okay? Because it's just spread out so far. And so that becomes its own logistical challenge. Like, it isn't like, hey, we're in a near Earth orbit where the intensity is still pretty strong. This stuff is spread way out. So, on 68, because you're a long way away. So, you're broadcasting with 21 watts of power, assuming transmitted broadcast in all directions. What signal intensity was received on the Earth? So your answer to 68 should be around something times 10 to the minus 26.
6?
Minus 26.
for 8?
Yeah, negative 26, so we're good.
Okay, we got that bird.
Okay. Which is a really, 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 really small amount of energy per square meter. Because that signal, we're so far away, we're transmitting it back to the Earth, that's a really, really weak signal. Then on B, on 68, what electrical field amplitude was detected? So now that you know the intensity, to do B, you need to do I equals 1/2 C epsilon naught times E naught squared and solve for E naught, and you should get a similar numeric answer to 68A, but 10 to the negative 12.
Where's the Sputnik now, or whatever it's called? Like, is it so far away that we,
Sputnik?
whatever it's called?
Voyager?
Voyager, that one, yeah, Voyager. Whichever
it's,
one.
It's way, way, way. I'm not sure exactly.
Is it probably just dead?
Isn't it near Pluto right now?
Pluto? I feel like it's probably way, yeah, past Pluto. Like, I don't even know if, like, enough of the sun's heat.
I just did it all in one calculation. I didn't do it. But it's
So it's just going out there
4.5
in the
times 10
middle
to
of
the
the
12 squared times 4 pi.
That's what I heard. Oh, it's 10 to the 12. Then it's 209. Oh,
I thought it was like.
But most
Wait, actually.
Those two are the same.
I'm not catching that.
Yeah. Oh, I got that number.
Okay.
And what, you divide that by that?
Right now, as of April 2026, Voyager 1 is 15.7 billion miles away from Earth.
Oh, I forgot to finish my.
38,000 miles an hour. It takes a day for a signal to.
So, it's a long way.
when is it finding aliens?
We're probably not. So, anyway. All right, are we good?
Wait. I have a question.
Wait.
Hold on. 24, question 24.
The true-false question?
What's true or false?
Question or problem 24?
Question.
What about the true false?
Guys, I got
23 and 24.
The one with like all the letters and like
Which one is
you
true?
hit which one's true or false or whatever.
24 is B.
And C.
No, it's
So-
not.
Is it like 3 letters?
Whoa, we had true and false?
On 24.
I just-
On 24.
Yeah, your book.
Not that picture, but
On question 24,
Gavin has his book.
says which of the following, perhaps more than one, are true.
Oh, those.
Okay? So on 24, let me give you a hint. 2 of them are true.
Oh, I got 3.
Can you explain how C
Oh,
is true?
So let's look at your options on 24. So, and this is going to be important about what we're going to talk about today with the photoelectric effect. So the frequency of a light beam is increased, but the light's intensity is unchanged. So intensity is basically, hey, how bright is this thing shining? So is frequency going to alter the speed of the photons? No. So it can't, 24A can't be false.
Oh, yeah.
Now, what about the photon has more energy? True, because frequency and energy are directly proportional. Right? Then you get C, there are fewer photons per second. Now, when you look at intensity, intensity is as important as you understand that intensity is measured in joules per second, which is the same thing as watts. Okay? So, here's the best analogy I can give you. You want this watts to be the same. Okay? So, I'm sorry, they're talking about intensity. So, the intensity is unchanged, which is watts per square meter, but watts is joules per second. So basically, you're going to keep everything here the same. So if you look at this in terms of photons, so as soon as you shrink the frequency, or excuse me, as you increase the frequency, that means that each photon that strikes that surface is going to carry more energy. Okay? Well, if you keep the same number of particles hitting the surface, and each of them have more energy, what's going to happen to your intensity?
Up.
It's going to go up because you're going to have the same number of photons hitting with more energy, so you're going to have more energy per square meter. So the only way that you can keep the same intensity if they have more energy is to decrease the number of photons that are striking it per second. Okay? That makes sense. All right. What?
Does volts per meter stand? Like, what is volts per meter?
That's your measure of your electric field.
Is that joules?
Huh?
Is it the same thing as joules?
No.
Yeah.
Yeah. No, it's just volts per meter.
That's E.
Yeah. Because remember, voltage like equals ed. So your electric field is volts over distance, which is in meters.
Yeah, we do the simplest thing.
I'm tired of this.
Okay. Anything else? Then once or twice sold. Give that handy in popcorn. Can you stop that?